Okay, we're back doing some mechanics. In particular, we'll be using conservation of energy and do a couple of examples of finding speeds. So generally, we make it a point that there's two main ways that we can find the motion of objects as far as calculating them and understanding them. And that's through Newton's laws, which use forces and energy. Now, Newton's laws, of course, deal with vectors and differential equations. Energy, by and large, being a conserved quantity and also a scalar, is a little bit easier to work with. So, at the same time, having said that, energy also doesn't help most of the time if we're trying to find things like the acceleration of objects, or trying to find some forces. It kind of depends on what you're given in the problem. But generally, if those are what we have to find, then we're kind of stuck with F equals ma. However, if we need to find speeds of objects, energy is usually the one that I would suggest trying first. If you have the information to use energy, go for it. It's going to be easier to work with in the vast majority of cases. So that the conservation of energy really is telling us that we have to figure out how much energy the problem starts with. Okay, potential and kinetic. In this case, we're kind of assuming that there's no external forces, no work being done on the system. And then, the final totals of these, now we have to include heat. We're going to deal with friction here in one of our examples. Now, heat basically refers to the fact that it's the work done by friction. So your friction force times the distance that the friction is acting. Okay, but that in general is kind of our shell that we use to set up problems. So here's one case where we're dealing with springs, along with friction, and along with hills. Okay, so we're mixing a bunch of stuff together. There's friction everywhere. A spring, just in its own right, is a non-constant force. So that alone would make Newton's laws kind of difficult to make use of. You'd have to do some calculus. Try to avoid that if you can. So what we're saying is, we're going to assume that we're going to use the spring to launch a little mass. It's going to slide and go up the hill, and our job is to figure out where does it stop. So what's its final position or final height up on the hill, assuming that it makes it that far. So we're going to have to compress the spring a certain distance. We're calling that distance b in this picture. And then it's going to launch it, it's going to slide and go up the hill, all the while losing some kinetic energy to heat because there's friction involved. Okay, so looking at our conservation equation up there, we're starting off with just the energy of the spring when it's all compressed. 1/2 kx squared, or in this case we plug in the x value. There is no initial kinetic energy, it's starting off at rest. So that's our total. And now we ask the question, well, where does that energy go? How does it get distributed? Okay, well, there's a couple things we could do with this. One thing would be, how fast is it going by the time it gets to the hill? That might be the question. If that's the question, then obviously some of our kinetic energy is going to go into, or some of our potential energy of the spring will go into the kinetic energy. Okay, but then it hasn't changed height or anything, so there's no potential energy that we're dealing with, but there will be heat. So we'll have to include the friction force times distance. Friction force is muffin, so that's our coefficient times the weight, because we're on a flat surface, times the total distance that it's going to slide, and that looks like it's going to be L plus B. That's what our energy equation looks like, and we could actually go ahead and solve for the speed out of that kinetic energy term. Now, what if the problem is to figure out what the final height is on the ramp? Okay, well, if we could just do this right from the start. This is our second thing we're trying to find. we're going to take all that initial energy of the spring and say, okay, well, where does it go? Well, by the time it gets to its highest point up here, if it's at the highest point, that means that it has stopped. So there is no kinetic energy. There will be potential energy now because we're up on a hill. We can just use mgh for that. But some energy went into all that heat due to the friction. So here's a case where we're going to have to figure out, okay, well, we have friction on the flat surface. So we're going to lose some heat there. And now we're also going to have to account for the heat as it goes up the hill. Now for friction, because friction is running parallel to the hill, we need to know, well, what is that diagonal distance that it goes? Plus, the normal force is different on a hill. So the normal force, or the friction force is going to be times normal force. So that's going to be mg cosine of the angle of the hill. Now the diagonal distance that friction is acting on, what's that looking like? That's going to be whatever your final height is divided by the sine of the angle. Okay, so that's what the equation looks like. We have two terms with the final height in it. We'd have to do some algebra in order to solve for that, but it's doable. It's a little bit of algebra. This would be tougher if we're using Newton's laws because just the spring alone would cause issues. We'd have to figure out a differential equation for a spring to figure out how it launches it. So energy is the way to go in something like this. A second example where you have a non-constant force is something involving gravity but with big heights. Okay, satellites, planets, things like that. So here's a case. Let's say that we launch a space probe, a little satellite or something. Something goes wrong and its engines fail. And it starts off at rest some big height above a planet. Okay, we want to figure out by the time it hits the planet, way down here, how fast is it going? So using Newton's law, this is a non-constant acceleration. We'd have to do some work and use some calculus to figure out how to get that speed. But energy gives us a way out, a very straightforward way. Now it starts off with some potential energy because it's at rest. Now to do potential energy due to gravity the right way, we've got this generic expression here, negative gmm over r. Okay. So in this situation, your initial potential energy, it's always negative g, the mass of the satellite, times the mass of the planet. And it looks like, relative to the center of the planet, we're a total of 3r. 3 of the planet's radius above the planet, or above the center. Where does that energy go? Well, by the time you get to the surface down here, relative to the center of the planet, you still have potential energy. It's just one radius of the planet. But now we have kinetic energy. Kinetic energy is always a positive. Now if we're falling through, I put the condition here, there's no atmosphere, there's no heat being lost or developed as it falls. And so that would be it. And we could find the speed out of that kinetic term. Okay. So again, I'm not going to worry about the algebra. I'm really worried about the setup. We're using conservation of energy to deal with non-constant forces and to find speeds. It's a whole lot easier than using Newton's laws in F equals ma, which would deal with calculus, vectors, components, all that weird stuff that just complicates matters. Okay, and it all stems from a pretty simple equation up here. Your total energy before is equal to your total energy after, as long as no work is being done on the system. And that's how we can get by, okay, in a much easier way. So I hope this helps, and until next time, we'll see you later.